Okay, good morning all. I hope all you are doing well, healthy in these days. Again, we are living in difficult days at the moment. I hope we are gonna cope with all these issues. Today is the last subject for the statics course. We are gonna run the moment of inertia subject, which is all these subjects are really important that we talked previously in this session, in this course. But today, we're going to learn about how to calculate the moment of inertia section. Why this is important? This is important because in the second term, in the spring term, we are going to do the strength of materials course altogether. That's why we will use this moment of inertia subject almost each main subject in the strength of materials course. So that means if you can't calculate this moment of inertia, you can't do anything in that course. Even if you understand the subject, what I explained. So at the end of the day, we are doing a calculation process. In some part of this process, we have to use this moment of inertia. That's why this subject is the last one in the statics course. After that, we are going to close this term, and then we are going to run the new term. So this last subject is a connection subject for the next term. Okay, you have to be careful this one. We are going to ask this subject in the exam. So this is a clue for you. So this is important. The main thing here is, by the way, the subject is very, very short today. I'm going to explain everything with the examples. Okay, at the beginning, I'm going to try to explain, but I guess you're not understand this one. When I solve problems, you are going to get better understanding of the subject. So that's why please try to listen me and try to understand. After I solve the problems, before next week, please do a few examples by yourself to understand what we are doing, because next week we are going to solve examples about not only for the moment of inertia and about all other subjects. We will recap all of them before the final exam. Next week is the last week for us. That's why please try to do this subject by yourself before the next week. Because if you have any question, any queries, any difficulties, please ask me. Okay, let's get started. Here we have the line again. Subject is moment of inertia. Okay, what is this? Okay, we will do some mathematical calculations. That's okay. We are gonna get this moment of inertia as a number, but what it is, we need to understand that first. It's a kind of section property which resists for the deformation. Let me give you an example. If I find my ruler here, where is it? Okay, this is the book. Okay, this is my structural number, structural B. Okay, so you can see here my beam. I have here one support and another support is here. Okay. Just think about this one. my beam. Under the vertical loading, my beam will get this shape. It's gonna get a deformation under this vertical loading. Okay, under this vertical loading. So when I apply this load, it gets this shape. What is the section of this beam? Section is, which is perpendicular to this member. My section is this, as you can see. Here, there's a long edge and a short edge, as you can see. When I apply the load, you can see the deformation, basically. Let's change our structural member, this one. If I apply a load here, can I make a deformation? It's really difficult. You can try it yourself. Take a book and try to make a deformation. Here you can see, you can deform it. But if you take this book like this in your hands, when you apply load here, can you get a deformation? By the way, the section is same, as you can see. When we cut the system, you are gonna see this one. When it was like this, the section was again this. What is the difference? Okay. We are gonna talk about these differences. The section is same, but if it's in lateral position, I can deform it. In vertical position, it's not easy to deform it. You can see, you can't do that by your hands. It's not easy. Okay, let's talk about that. Here, question was like this. I have a vertical load on the beam. Section was here. The first section, A section, was like this. And this is the first one. Second one is, it was like this. Okay, these are the AA sections. This is the second option. Here, what we have, when we cut the system from here, if we look at this beam in this AA direction, I see this one. So where is the load here? Where is the load here? Load acts on top of this section like this in the first option. And the second option, it acts like this. Okay, in this direction. So what we get after this small experimental study in our hands, if we have the section is same, the section is same. Let's say this dimension is B, or this is X, this is Y, this is X, this is Y. So dimensions are same, but when we change the orientation of the section, we get a really big capacity which resists the deformation. So this is coming from the moment of inertia. If you check the moment of inertia in this direction of this section, and then if you compare it with this one, the option 2 has really big moment of inertia value than the option 1. So if we have big moment of inertia, so it right here, moment of inertia, if this increase, resisting to deformation increase. Yeah. If our deformation resisting increase, you can use this concept in your structural design. Nobody wants to have really big deformations in their design. Okay. While we are designing structures, what we are doing, firstly, we check strength. That's okay. We check it. Strength is important. We are going to see how to check the strength in the next term. And then we check deformation. So deformation should be less than a limit value. So very large deformations is not good for a structure. Okay. So this moment of inertia is a sectional property which represents the section's resistance for deformation. So today we're gonna learn how to calculate it. Let me draw a section. Bu arkadaşlar deformasyona karşı koyan bir kesip özelliğidir. Bunun nasıl hesaplandığını göreceğiz şimdi. Attachment momenti artarsa, by the way, the moment of inertia is in Turkish, atalet momenti. Atalet momenti artarsa deformasyona karşı direncimiz de artıyor. Daha az deformasyon yapıyoruz. Okay. Sorry for Turkish. If you have any Turkish book, you can check it in the attachment moment subject. This is X, this is Y. If I have a section, this is the area of the section, and this small rectangle area is dA. We are dealing with a small area, and here we have X and Y. This one, this part is X. Here is Y. Here is Y. And if we need the next stage, this distance is R. Okay. The moment of inertia with respect to x-axis is Ix. By the way, the I is the moment of inertia. Okay, we use this capital I for representing the moment of inertia in our calculations. Capital I. Okay, if we are doing for x-axis, Ix, we use Ix. Okay, Ix equals integral y square times dA. What does this mean? Okay, consider this small area. This orange area. And we have the center point of this area, yes. Area of this small member times the distance, the axis that we are dealing with, which is X, because we write it here. What is the distance to x-axis? Y, right? Area times distance square gives me the moment of inertia for that X. It's same for the Y. Okay, this is the general explanation. That's why I'm just using here the integral. In the next stage, I'm going to give you a few pre-calculated formulations you have to know. If you know that formulations, you can solve the problems. You have to do any you don't have to do any integral calculation here, but to explain the problem, I have to use this mathematical terms here. Let's do it for y. y. I'm going to calculate the moment of inertia for y-axis. Okay, integral. What was the rule? Area times distance square. Okay, we are at the midpoint of the A. So we're going to calculate the moment of inertia for y-axis. What's the distance to the y-axis? As you can see, it's x. X is the distance. What was the rule? Area times distance square. Okay, distance is x square times area. This is the definition of I, Y. So general definition, I is the area times distance. Okay. And by the way, the perpendicular. So this is the general idea behind all these Ix and Iy. Okay. Now we know what the moment of inertia is. Okay. Basically, we know the basic term where we use it. Now we know the mathematical equation. So there's one more important sectional property, which is radius of variation. Yeah, by the way, this is before I jump to a new subject. I'm not right here. Radius of gyration. It's the small I is I moment of inertia over area and total square root of this number. What is this? Radius. Oh. Let me write the Turkish form. It's atalet yarıçapı. Okay. This is in Turkish atalet yarıçapı. Okay. This is the general form of this radius of variation, where we use it. In the next term, we are going to use it for the buckling of the structural members. Okay, while we are calculating the buckling capacity of the columns, vertical struts, we are going to use this radius of variation. It's atalet yarıçapı. We can calculate it for x-axis or y-axis. So here, if we are doing a calculation for x-axis, what we do, we use Ix, okay, over A. And if we have y-axis here, what we are going to do, this is Iy over A. This is the these are the radius of variations for the x and y axis. Okay, now I know all these data are flying objects for you. we are gonna put them together with the examples. Here, I'm trying to explain what they are. At the beginning, we talk about what's the meaning of moment of inertia. Okay, it's a kind of resistance for the deformation. If we have higher moment of inertia, we get smaller deformations. If we get small moment of inertia, so we get large deformations. Okay, we get large deformations. So here we learned how to calculate it. Area times distance square. Area times distance. Distance to where? Distance to where we want to get the moment of inertia. Okay. So now we are gonna talk about the parallel axis theory. There is one more theory here, and then I will give you the moment of inertia of simple geometries like sphere, like rectangle. So then we will solve a few problems. Okay, let's do the parallel axis theory. Okay, parallel axis theory. Okay, we can change the axis of the moment of inertia with a simple calculation, with a simple thing. For example, if I have a member like this, okay, and this is its x axis, this is x, and what I have here, this is the g. Okay, this is the g, and what I have here, ix. What I have here, ix. The ix is the moment of inertia of this section according to this x-axis. Ix. So if I want to change the location of this, or if I want to change the moment of inertia values according to a new axis, which is here. This is a new axis, x prime. Okay. So then, okay, I have the moment of inertia according to this axis. That's okay. I have this one, but I need a moment of inertia according to this new axis. Let me change the color. Maybe that's gonna be good. X prime. In my calculations, I'd like to use the moment of inertia of this arbitrary shape according to this x prime. X prime. Okay. So what I need to calculate this ix prime. How to do it? So when we do this change, by the way, these lines should be parallel to each other. Okay, we can do it in between parallel lines, because as you can see, the name of the theory, you can see parallel axis theory. Okay, what is the distance between these two x? D. Let's say the distance is d. Now, let me write the equation here. Ix prime equals here. write all the equation. I'm going to give you the result. That's better. I x prime equals I x times plus area times b square. This is the area. Okay, what we did here. Remember, what was the definition of the moment of inertia? While we are calculating a moment of inertia, we were using the area and distance square and multiply it. Okay. Area times distance square. So here, what we have, in the first position on the x-axis, we have the moment of inertia. We know it. We can calculate it. But we need to shift that Ix to for the new axis, x prime. So what we are doing here, this is the new one. This is the existing moment of inertia plus area of this one, area times distance square. Okay, area times distance square. So here, as you can see, here we have moment of inertia definition. Okay, just a second, guys. I'm gonna join again. There's a home issue, as you can hear from here. Just a second. I need to solve the problem. I'm sorry for interruption. Yes, we were. Okay, we have here Ix prime equals Ix existing plus A times D square. That gives us the new moment of inertia on the parallel axis. So you're gonna see how we use it. This is the parallel axis theory. Okay, how we solve the complex shapes? How we calculate the complex shapes moment of inertia? For example, complex shapes. Here you can see here here. Okay, we have this section. This section is like total section. Okay, here we have a gap. Okay. Okay. If we have this kind of shape, how we can calculate the moment of inertia? I'm not gonna make a calculation here. I'm gonna give a logic to make these calculations. Okay, remember to calculate the centroid point, what we were doing, we were splitting these complex shapes to basic shapes. Okay, we are gonna convert these shapes to basic ones, and then we will calculate their moment of inertia values one by one. If we need, we have to shift their axis to X or Y axis at the end of the day. For example, for this shape, what I'd like to get IX and IY. So IX and IY, as you can see on the section. By the way, here there is an opening. This is an opening. As you can see here, there's a hole on the section. There is a small part, which is not here, as you can see, at this region. So we need to, for example, let's change the color. Let's divide this section. For example, I have a triangle here. So if I connect this part to each other, totally, I have a rectangle here, which is one. Here I have a triangle, 2. Here I have a missing part, as you can see, a missing part. Kind of, we don't have material here. This is 3. There is an opening, there is a hole here. This is 4. So what I have 1, 2, 3, 4, 4 different simple shapes. So I will calculate each member's moment of inertia according to, for example, x-axis. While I'm doing that, I'm going to use this parallel axis theory. If I have a missing part or opening, I have to remove it from the total. Okay, remember, it's like a centroid calculation. If I have a missing part on the section, a hole, an opening, whatever, where I don't have any material on that portion, I remove it from the total. Okay. I remove the moment of inertia of this circle at the middle. I take it out. So this is the logic behind the complex shapes. So here, I'm gonna give you the basic shapes, moment of inertia values. Okay. Then I will do examples. I know you're gonna get better understanding while we are doing these examples. Okay. While we are doing these examples. Okay. Basic shapes. The most well-known one is rectangle. Okay, rectangle. If I have a rectangle, please take a look at this part, try to understand what I'm doing. So the equation is really basic, but you need to understand the logic. Here, this is X, this is Y. So this dimension is B, this dimension is vertical one, H. Okay. if I'd like to calculate Ix, okay, I'm gonna do this for the x-axis. What is the rule? The edge, which is parallel to the axis we consider. Take its dimension, which is b, times the edge dimension, which is perpendicular to the axis we consider at the moment, h. It's cube, okay, over what? This is for the rectangles. Okay. Okay. If you do this for y-axis, okay, for y-axis, iy. Let's use the same rule. So take into account first the edge dimension, which is parallel to the axis. We are dealing with y-axis. Y is here. The parallel edge is h times the edge which is perpendicular to the y-axis, b, and its cube. Parallels directly comes here, and perpendicular comes here with cubic value. This is for rectangle. So you can memorize these equations, which is like b times h cubed over 12, or h times b cubed over 12. That's okay. But when we change the shape of the system, you can mix them each other. That's why the basic logic is like this. If we are dealing with the parallel edge, it comes as it is. If we have a perpendicular edge, it comes with cubic value. Okay, that's the main idea in this rectangle. Okay, next is triangle. Next is triangle. So what we have, this is B. And this H. So here, for X. For example, if you like to get IX, which is almost similar to the rectangle. Okay. This is for triangle. And the last basic shape for us is circle. So here we have circle, and we have a radius which defines circle R. So IX, right here, X and Y axis. Here we have circle in each direction each direction we have same radius. That means we have same sectional property. We have same moment of inertia for each direction. But basically here, we are gonna say Ix and Iy. That's okay. Because we are doing our calculations in X and Y axis here in this course. This is Ix, which equals Iy. What is it? It's P times R over 4 over 4. Okay. This is the moment of inertia of a circle. Now, what we have a rectangle, we have triangle, we have circle. You have to know all these basic moment of inertia values, equations. So, if you don't know, you can solve any problem. Okay, the subject is this. There's no more subject. After this time, I'm gonna solve examples to explain how to calculate moment of inertia. Okay, here, as you can see, we have rectangle, triangle, circle. That's okay, good, but we generally deal with complex shapes. Not always these basic shapes. That's why I will solve you a few problems. So let's do our first example. L-shaped section. Okay. And motions here. Something. Here we have something. Okay, what we have? We need this one, I guess. We need this dimension. Okay. Now, what is the question? Okay. Calculate the Ix and Iy, which respect to the axis goes from the centroid of the section. Okay. This is the question. What it says. Ağırlık merkezinden geçen eksen takımına göre Ix ve Iy, Iy değerlerini bulunuz. Okay. What we have. So there is no axis system on the section, as you can see. But the question says to us, okay, find the centroid and put an axis system to that centroid point, x and y axis. The horizontal one is x, vertical one y. And according to these x and y axis, calculate the IY and IX. Okay, that's the case. That's the case. We have a charge problem. Okay, what we have, we can split this section two pieces, basically. We have L-shaped section, so we can split it to simple sections. What are they? They are rectangles. Okay, they are rectangles here. So let's do it together. Let me divide system. I don't know. We can divide like this or like this. I don't have the solution at the moment. We will solve it together. Let's do it like this. Okay. Now, to calculate centroid, we need an origin point. Let's say we are going to calculate the location of centroid according to this point. Okay. Let's do it to x. Okay, what I have here, I have a rectangle. Its area is, okay, this one, times the center point of this number is here. Distance to this line is 12. By the way, I'm doing y. I'm doing first y in the vertical direction. Okay, this is the area times distance to this line plus what is the area for this part? Here is 13, as you can see. Here is 13. Okay, 13 times 2, area of this part. 13 times 2 times distance, vertical distance is 1. Over here. Okay. Over here. What? Total area. Total area is plus this one. Okay. This gives us the location of y. Let me calculate it. Times plus over yes. Okay. This is the y distance. Okay. Centroid is here. By the way, this is the centroid. Here is y. Here is x. Okay. We are just calculating this x and y. Let's do it for x. Area here is for this one again times distance to this vertical line in x direction, which is 1, plus area here is again distance to this point. This point is this line actually. The center point is here. Center point is here. Half of that one is 6.5 plus 2, 8.5 over total area. I think you know how to calculate centroid. You don't have to do it like this. You can use our method, table method, to calculate centroid. That's okay. It depends on you. I'm just doing this fast method here. Let me calculate total plus yes, this one is the x is 3.63, y is 8.13. Okay, we have now these distances. Now, my axis system is now here, according to the question. Question says put the axis system to the centroid point and then calculate the moment of inertia. Now we are gonna do first Ix. Okay, Ix. So let's take a look to first shape, which is rectangle. So what we are gonna do here, we have a center point of this rectangle. We are gonna calculate the moment of inertia according to this point. Then we will shift this moment of inertia to the global x-axis. We are going to calculate first for the local x-axis. Then we are going to shift it to the global x-axis, where we are going to use the parallel axis theory. Now let's read. For this rectangle, this is the, by the way, this is the local x-axis, this is the local y-axis. Okay, these are the small axes. What is the moment of inertia for this one? Let's write it here. 2 times okay, 2 times this. This is the moment of inertia of this rectangle. And what was the parallel axis theory? We add this one. Area times the distance between two parallel axes. Okay, area is here. This is the area times. So the distance between these two axes. How we can calculate it? If this is our baseline, if here is our baseline, this is 12. And what is this? What is y? Y is, let's write here. the differences between these two distance gives me this one. So right here, minus. Okay, we have just calculated the moment of inertia for the first rectangle. Plus, we have just calculated for number 1. This is number 2. Let's do it for the second one. Let's change the color. Plus. Okay, we continue from here. What we have? We have a rectangle again. The x-axis, it has a local x-axis, x and y. We are going to do our calculations according to this local axis, and then we will shift it to the global one. So x-axis, don't forget this one. Here, parallel edge is this. What is the distance? Which is 12 times perpendicular is 2, and it's cube over 12. What we have? We have the moment of inertia according to its local axis. Now we are going to use the parallel axis theory and shift this local moment of inertia to the global axis. Plus area times distance square. Area is this one times distance. Distance is the y is here from this baseline to the x-axis. This is y, as you can see, and we know the center of this rectangle at the mid portion of this 2. So what is this? This one minus 1 square. This gives me Ix. Okay. This gives me Ix. And let's do it. We can calculate it with our calculator. It's easy. Firstly, let's write the equations for Iy. Now, where is the y-axis? Y-axis here in the vertical direction. Vertical direction. So again, we are on the member 1 here. So we are going to do our calculations for the local y-axis. Okay, careful here. What we were doing. So local y-axis is here. Parallel edge is here. What? 24 times perpendicular one, 2, and it's cube. 2 cube over 12. This is the basic rectangle's moment of inertia. And we are now on this local y-axis. We will shift this local y-axis value to here, global axis. Distance between the local and the global one is required here. We are going to do it. Plus area. Area is area, basically, as you can see at the top. 24 times 2. Okay, 24 times 2 times distance square. Distance. We know the x. We know the x here. X minus half of this edge gives me distance between this local centroid and the global centroid. So let's do it. X is here 3.64, let's say 64 minus 1, because we know the center of this section is at the half point of this or midpoint of this dimension. So it's 1. The x minus 1, 1 is here, gives us distance square. Okay, this is the member 1. Let's do it for member 2. Here we have a rectangle. Here we have a rectangle. It has a local y-axis. It has a local y-axis. So we are gonna do our calculations according to this one. Let's do it first. Parallel edge is 2 times perpendicular one is 13, right? 13 cube over plus. Now we are on this y-axis and we are going to shift it to the global one. What we need, the distance between two y-axes. By the way, let's write the area first. This is the area times distance. Okay. From this baseline, if you assume this is our baseline, what is the distance of the centroid of this member 2? Basically 6.5 plus 2. So 8.5 minus x. Okay, this is the IY. So we can get the results here and here. Let me calculate. I don't have the results. That's why I will do it with you here. Actually, you can do it yourself. Times 2. Right, the small here. That's great. I hope I'm not doing something wrong. Here. Yes, these are the numbers. Okay, let's sum all these numbers. Plus. Yes, the number here, the result. Okay, here, be careful. Unit of the moment of inertia is the fourth power of the distance or length, because here we have basically this is a length, this is a length. This cubic form comes here and one power comes here. Totally, this unit is length fourth power. Okay, we have this one. This is the Ix. Let's do it for the Iy. I'm gonna calculate it for this time. Next time, I'm gonna write equation and you can calculate it by yourself. Here. Here what we have. Here. This one is okay, 2 times last one is okay, let me make this summation. Okay, this is the Iy. Okay, here we have Ix and Iy values of a basic shape. This shape is really basic because there are only 2 rectangles on this shape. What you can do more, for example, instead of split it to 2 pieces, this is like this, right? You can do also, it depends on you. There is no one-way solution. You can do it in a different way. For example, you can complete it to a total rectangle. This is your shape. This is the missing part, and calculate the total rectangle's moment of inertia and remove this part. It's possible. It's another solution. Okay, but at the end of the day, you are going to get these solutions. The method is different and the solution is same. So we are going to solve a few more problems in the next session. Let's have a break of an hour. It's 10 past 20. We're going to be here 10 past 50. Okay. We're going to be here. See you guys. Hi, Leah. Okay, and then solve a new example here. a T section. So dimensions here. Okay, the first question is find center rate and B is calculate I, X, I, Y, X, to axis system. Centered. Here we have a T section with the dimensions given on the sketch. The first thing, calculate the center rate. I think you know how to calculate it. Then find the center rate point, put their global axis system. Then calculate Ix, Iy, and radius of gyrations for X and Y axis. Okay. Okay. Let's do the center rate first. Here is vertical straight line. When we look at this system, to define the center rate, we need X and Y coordinates, right? So when we take a look at this T section, it's completely symmetrical section around the Y-axis, around the vertical axis. So we know that if we have a symmetrical system like this, the X will be at the middle, XG. So XG is 0 if we assume an axis like this. This is this one. So we are going to be at the midpoint. We need what? Sorry. We need Y coordinate because we know that the centroid will be at the mid portion on this line, but where? At which level? So we are going to see it. YG is important for us. YG is important for us. If we divide this system two portions from here, okay, we have a G1 here and G2 here. We have two different centroids, local centroids, but at the end we are going to calculate the global one. Okay, local is coming from these separate rectangles. But at the end, we are going to calculate centroid of this T section. YG, area times area. First, let's write the area. Area is, this is 15 times 4, area times distance. Distance is what? Distance to this baseline. Where is the baseline? We are going to calculate the YG. That's why we calculate distance from this baseline. So here, what we have, 12 plus half of this total height, 14. This is 14. Okay, it's 14 plus area. Area is 12 times 3. 12 times 3 times distance is here. Half of this height of this rectangle. Total is 12. Half of it is 6. Put here a 6 over the total area. Total area is this 15 times 4 plus 12 times 3. If you do this equation, what you are gonna get? You are gonna get 11. So what does it mean? It means our centroid is over here. Oh, let's change color. This is G. This is global G. The centroid of this T section. Okay, we know this one. This is 11 centimeter above this baseline. This is 11. So we know the centroid location at the moment. Let's check the first one. Let's do the second one. Put an axis system to this centroid. What is it? An axis system. So here, this is X. This is Y. Okay, this is the global system. Okay. Each system has their own one. For example, for the G1 or first member, let's say we have an X and Y here and another X and Y here. The logic is that firstly, we do our calculations for the basic shapes, local coordinates, local centroids. That's okay. Then we transfer it to the global axis. Do it local and then transfer it there. Shift it the local to global. This is the logic. If you understand this one, you can solve every problem. Now let's write the IX. Moment of inertia according to x-axis. Now we have the first member, the top rectangle. So for the x, let's write its moment of inertia. I'm gonna write this equation again, step by step, slowly. I think you get better understanding of to calculate this moment of inertia with this method. Sorry. So we have this one. Okay. What is the parallel edge here? Parallel one is this one. Totally 15 times what one? Which one is the perpendicular? Perpendicular is this one. So 4 cube. If we have a perpendicular edge, we get cube over 12. This is the moment of inertia of this rectangle at the top. Okay, this is for the local coordinate system. Now we are gonna transfer it to the global one, to the orange one. Okay, plus we add something. What? Area times distance square. Area of that rectangle. So it's 15 times 4 times distance. Okay, what is the distance? The total G location to the baseline. The baseline is here. So totally 12 plus 2, 14, 14, 12 plus 2, 14. Yes, we know this is 14, but the global centroid is at 15. So the distance is 14 minus 11 square. Yes, we've just completed the first rectangle, first one. Okay, first one. Let's do the second one. This one. So, according to its local axis, the parallel edge is 3 here, 3 times height of the rectangle, which is perpendicular to the axis, 12 cube over 12. Now, where are we? We are on the local axis of the second rectangle. We are here now. We need to transfer it to above, to the orange axis system. Yes, we can do it. Plus area times distance square. Area of the second rectangle is 12 times 3 times distance. Okay. Here, distance is 11. 11 minus 6 square. 11 minus 6 square. So, yes, that's it. Here is 3, here is 5, and the result is here. (1,952 centimeter over 4). Any question regarding this IX? No, I think. Okay. Please do these examples by yourself. Don't forget to do this by yourself. Otherwise, you cannot understand anything. How to calculate moment of inertia. Now, let's do IY. IY. Change color. IY. So, what is the logic? We are going to calculate the moment of inertia according to the local axis, then transfer it to the global axis. Okay. So, for the rectangle at the top, what is the parallel edge? Parallel edge, which is the parallel edge is, because we are dealing with y-axis now. Okay. Parallel edge is this. It's 4 times the perpendicular one is here. Totally is 15 cube over 12. We are now on the local y-axis. What are we going to do now? We are going to transfer it to the global y-axis, the orange one. We are on the blue y-axis for the first, the top rectangle. We're going to transfer it to the orange one. How we are going to transfer it? So when we have a look to sketch, you can see the local y-axis and the global one coincide. Okay, one is on top of the other one. They're on the same line. So here, we don't have to transfer any moment of inertia somewhere else because we are already on the global y-axis. Okay, since we are on the global y-axis, we are not going to transfer it. This moment of inertia, this calculated one, is the local moment of inertia, and at the same time, it's global moment of inertia for this one. Okay, let's have a look at the second one. We have second, the bottom rectangle. Let's do this procedure for that. So we are dealing with y-axis. The parallel edge is 12 times perpendicular one is 3 cubed over 12. Now what we have the moment of inertia of the second rectangle according to its local axis. Are we gonna transfer it? Let me check. When we look at the sketch again, for the second or bottom rectangle, again, we have a coincide y-axis. Okay, our local y-axis coincides with the global one. That's why we don't have to shift anything else because we are on the global y-axis. So this is my total IY. If we check the result, it's okay. Now we have IX and IY. We did IX, IY. Now we are gonna do the radius of gyration. So what was I'm gonna do it here. What was the equation? EX equals total IX over A. So let me calculate the area. Area is here. Plus this is the area, which is 96 centimeter square. So let's calculate the x here, ix here over this one, and it's same for the y axis. Here we use IY. Yes. The results are, let me check. Centimeter. Okay, here we have a rectangle at T sections, moment of inertia and radius of gyration calculation. Check any other examples. What I have here. you need to, while you are studying about some, you need to get better understanding of when we shift or when we transfer a local moment of inertia to global one, and when we don't. If you understand these differences, so you can solve each type of problem. The problem is not to calculate the local moment of inertia calculation. To calculate the global one, while you are doing it, you shift moment of inertia from somewhere else to another location. So we use a process with a method. That's okay. Don't memorize the questions. If you do it, you cannot solve the problems. Okay, don't memorize it. Try to understand the logic behind that. Okay. Here we go. Now I have one more. Question, I guess. Okay. One more example. Here we have a box section. Box section means there's an opening at the mid portion. Sections here. So here we have x-axis. This is x, and this is y. Dimensions are, yes, let's write. Here is 4, 11 centimeter. And then in the horizontal direction, here we have 3, 10, 10, 3. Okay. Okay. What we are looking for? We are looking for the I, X, and I, Y. Okay. Now, we have the section at the mid portion. We have an opening. So, what we can do? You can adopt different methods. It's possible. You can divide this box section to different, for example, 4 different rectangular sections from here. Example. Change color. You can do it. Divide it from here, here, here. You have 1, 2, 3, 4. You have 4 different rectangular sections, and you can calculate the Ix. That's okay. What I'm gonna do here, I'm gonna assume that whole complete rectangle as 1. This is 1. And this opening is 2. Okay. I'm gonna remove this opening from the whole complete rectangle. Let's do it. Here, Ix. Firstly, we are dealing x-axis. We are calculating the whole rectangular section. That's why the parallel edge is here, this one. Here, this is the parallel to the x-axis. So total is 26 times perpendicular one. Perpendicular is 30, right? 22 plus 8, 30 cube over 12. Now we have the total moment of inertia. So the center point of the total rectangle coincides with the global axis system given on the sketch. That's why I'm not gonna shift anything else somewhere. There's no moment of inertia transfer here. Now I have the total moment of inertia. Now let's remove the second, number 2, second one, minus. Okay. Here, what we have again a rectangular section. The parallel edge is here, 20 times perpendicular, 22 cube over 12. Times 22 over 12. Again, I don't need to transfer any moment with using parallel axis theory because my local centroid point of these rectangles coincide with the global x and y axis system. That's why I don't transfer any moment of inertia. So now we get the equation, as you can see here, Ix. We calculated the completed rectangle, then remove the opening in the middle, as you can see with this equation, and we get Ix. Let me see the result. Ix here. By the way, the question I write here, wrong question. Ix and question answer. The source generation for x-axis, not Iy. But you can do it Iy by yourself. Now the result is this is the result. Okay, what is the radius of gyration? X kök square root of Ix over A. So A is here, but with A totally A here, minus this one. Let me calculate it. Here minus 340 centimeter square. Okay, So here, Ix, here the result is, check. This one. Okay, what we have X and X. Okay, while you are studying, please do the same things, I, Y, and radius of variation, Y. Calculate them by yourself. Okay, method is same. Be careful while you are doing Y-axis, which edge is parallel, which edge is perpendicular. Please be careful for that one. Okay, one more thing. Let's do one more question. Sure. Okay, we have section. So then, section, as you can see here, let me write the dimensions. Here, 4, 12, 4. 6, 4, 6 centimeters. Okay. Here we can see we have an x-axis and y-axis. Here's the center weight. Okay, good point. So, question is here. What is I, Y, and radius of duration for the y-axis? So, okay, we can do it. We can do it. Let's write the equation. Now, I, Y. So let's split section 3 pieces. Here, here. These two are completely same, identical rectangles. That's why I'm gonna make a calculation for one of them. Then I'm gonna add 2. I mean, I'm gonna multiply it with 2. So it represents these two rectangles. Let's do it. So for y-axis, which one is the parallel? Parallel is this. Okay, which one is? This is parallel. So here, 16 times perpendicular 4. Okay, I'm just doing this one for only one rectangle here, plus. So what I did this calculation according to my local y-axis. So I need to shift it from here to here. Okay, I need to shift it. That's why I need the area times distance square. Area is 16 times 4 times distance square. Distance is here, the half of this web height is 6, and half of this 2, it's 8 square. What I did, I just calculated the moment of inertia for one rectangle, for this one. So what I said at the beginning, we have two identical rectangles. That's why I'm gonna multiply this with 2. Okay, now I did this one. So what we have more, we have the web. We have the web. Okay. Now what we have, which one is the parallel? For the web part, 4 is parallel. Times, which one is perpendicular? 12. 12 over here is perpendicular to the axis. Here, 12 over 3 over 12. Okay. Now what I did here, I just calculated the moment of inertia according to the local axis of this portion, this web rectangular, which is here. Y-axis. Now, should I transfer this local moment of inertia to the global one? We need to check. When we check this part, as you can see, my local y-axis and the global y coincides to each other. That's why there is no distance between these two axes. If I'd like to transfer the moment of inertia, the distance is 0. So I can't shift anything. I can't transfer anything. So this moment of inertia calculated for the web, for the local axis, at the same time, that is the moment of inertia for the global axis system. So we don't shift or transfer any moment of inertia, and then we do this calculation. That's it. So the result here is now we have the IY. You can calculate IX by yourself. Okay, do it yourself, please. It's an example for you. It's extra training for you. Do it for IX. Now I'm going to calculate the radius of variation. I need area for this. Area is here. 2 times 2 is coming from the number of these vertical members. 2 times 4 times 16 plus web area is 12 times 4. If you do this calculation, let me do it. Here, 2 times 4 times 16 plus 2 2, 4, 16, 12, equals. Yes. This is the area. Okay, let's calculate the radius of variation y total I y over area. Here. I y equals. The result is here. Let me check it again. Yes, 7.13 centimeters. Okay, what we have here, IY and radius of variation for y-axis. How many questions we solved? 1, 2, 3. I can give you a question for study for yourself. Solve this one by yourself. This is an extra. Here. Okay. So here dimensions are 20 centimeters. Yes, this one. Okay, this is our section. Okay, question is find the center rate, first one, and calculate the IX. IX according to
axis. Okay, according to this question, you can see the section here with dimensions. Calculate the centroid, where it is. Okay, where it is, and put centroid axis system. And according to this axis system, calculate the IX. If you like, you can calculate IY. Okay. But here in this question, we are looking for IX. The results, to check your calculations, I'd like to give you the result. YG, centroid location in the vertical direction. You know, in the horizontal direction, this section is symmetrical section. That's why the XG is at the midpoint. So YG is important here. YG is 5 centimeters from the bottom baseline, reference line or baseline, whatever. And IX is change the result just a second. The unit is different here. I changed to converted to centimeter. Yes, this is the result. Please do it. This example here by yourself. If you have any trouble, please let me know. You can take them all together. I think that's all for this week. We now completed all the subjects at the moment. Okay. What we are gonna do next week, we are gonna solve the problems. Next week is the application week. We're gonna solve problems regarding the truss systems. We didn't solve many examples. We're gonna solve regarding the cables also with the moment of inertia. I think you get the point regarding this moment of inertia. The logic is same. Okay, the shape, geometry can be changed, that's okay. But the logic is same. If you understand what we are doing, the logic behind our calculations, you can solve every type of problem. I believe in you. That's why maybe we can solve one example for the moment of inertia. So, okay, I recommend you to join the class next week, because next week is the last session before the exam. We are gonna solve examples. If you have any questions, you are free to ask to me. We can discuss. Yes, that's all for this week. Thank you for your attendance. Take care of yourself. Have a good weekend. See you next week. Okay, bye-bye.
Thank you, Professor.